Hello, everyone. Once again, this is our collaborative work with Natalia Loukachevitch. And the subject of our research is comparison of genres in word sense disambiguation using automatically generated text collections. So, word sense disambiguation is the task that consists of assigning the correct sense of the polysemous word in a given context. Word sense disambiguation is used in many semantic-oriented applications, such as, for example, semantic information retrieval, machine translation, various knowledge graphs, and lexical semantic resources. And to achieve high performance, supervised word sense disambiguation algorithms require large sense annotated collections. But usually, the annotation of such collections demands considerable human expert effort, and it is very time consuming. So word sense disambiguation algorithms suffer from the problem that is called knowledge acquisition bottleneck. And one of the possible solutions to this problem is automatic generation of training collections and automatic labeling of those collections. And in our research, we present the method that relies on monosemous relatives approach to automatically generate and label training collections. So monosemous relatives are those unambiguous words and word phrases that are connected to the target ambiguous word through some semantic relation. And monosemous relatives approach is based on the substitution. So we find the text in which such relative is used. Then we substitute this word with the target polysemous word, and then we label this context with the sense of the monosemous relative. And usually semantic graphs such as WordNet are used as a source for such relatives. And in our case, we used Russian thesaurus, RuWordNet, to extract monosemous relatives. In the examples below, we present some of the monosemous relatives for the two senses of the polysemous word doctor. However, this method has some drawbacks. For example, some senses of the target polysemous word may not have monosemous relatives, and some contexts of monosemous relatives may add noise to the training data. And in our research, we tried to address those issues. Here is outline of our report today. First, we are going to describe the data that we use in our research, that is RuWordNet thesaurus and different corpora. Then we will tell you about the principal features of our algorithm, that is the distance to the monosemous relatives, the concept of Sensitiveness, and Similarity Scores. Then we will present step-by-step description of our algorithm. Also, then we will overview the methods, two methods of compiling training collections, and then we will demonstrate the results of our experiments with different training collections, different contextualized word embeddings. And finally, we will show some additional findings that concern the genres of training and test collections and their impact on the resulting performance of the word sense disambiguation systems. So in our research, as an underlying semantic network, we used RuWordNet thesaurus. It is a semantic network for the Russian language that has a WordNet-like structure. It consists of around 63,000 monosemous words and 2,892 polysemous words. We use this resource to extract semantic relations between polysemous words and their monosemous relatives. We also exploited this graph to measure the distance between polysemous words and its relatives. And also we have taken the sense inventory from this thesaurus. Now to the data sets that we use in our research. First, we use two different corpora which differ in genre. The first one is the news corpus, and it contains around 1 million news articles harvested from various news sources. And the next one is Taiga Proza.ru corpus. That is, Proza.ru is the segment of a very big corpus that is called Taiga. And Proza.ru corpus is compiled of the works of prose fiction. So we display on the slide the characteristics of those corpora. We use those corpus to investigate whether the genre of the training corpus has an impact on the performance on the test data set for word sense disambiguation systems. Next, to evaluate our algorithm of automatic training data collection, we used 3 distinct Russia 18 datasets for Russian. From these datasets, we have taken only those words and senses that have one-to-one correspondence with the senses in RuWordNet thesaurus. So we compiled a test dataset that consists of the context for 30 target ambiguous nouns, and each noun has 2 different senses. For convenience, we call this dataset Russia RuWordNet dataset. We also created a small dataset that consists of word sense definitions and examples of uses from Ozhegov dictionary for every target polysemous word. And each sense of a polysemous word has a definition and between 1 and 3 usage examples. And this training collection was used to train a baseline solution for the word sense disambiguation task. So next to our approach, in different works, synonyms, hyponyms, and hypernyms are used as monosemous relatives. They are located very close to the target polysemous word in a semantic graph, and that makes them more reliable monosemous relatives. So they don't require any sophisticated additional verification procedure. However, as we have already said, for some senses of polysemous words, we may not find such close relatives. And so the central idea of our method is that a training collection can be built not only with the direct relations like synonymy, hyponymy, hypernymy, but also with far more distant ones. For example, co-hyponyms, 2 steps or more hyponyms and hypernyms. So, for example, most contexts for the word krona, in the sense krona currency, match the context of the other words denoting currency, like angliski funt, pound sterling, because they have common hypernym valuta currency. So we can see that for the polysemous word krona, the context with its hyponyms, like angliski funt, they're good training examples. So we can add them to a training collection. And the advantage of our approach is that we can find a lot more monosemous relatives for target polysemous words on such distances. But the disadvantage is that we have to score all those relatives, and we need to check their context so that they will suit as training samples. And to measure the suitability of a monosemous candidate to display a target sense of a polysemous word, we exploit a notion of a synseth nest. The synseth nest consists of the synonyms to a target sense and known words from directly related synseths within 2 steps from a target polysemous word. And in the following example, we present a fragment of the synseth nest for a word taxa in the meaning breed of dog. Then another important part of our selection algorithm is a similarity score. We use similarity scores between a candidate monosemous relative and a synseth nest to evaluate how well this candidate can represent the sense of an ambiguous word. Moreover, we check similarity scores to the synseth nest for every monosemous relative, because a word described as monosemous in the thesaurus can actually have polysemous usage in a corpus. For example, the Russian word iriska, toffee, can also denote a nickname of Everton Football Club, the Toffees. So we can see that the usage of candidate monosemous relatives in the source corpus should be further checked, so it won't add any noise to the training collection. Now let us turn to our algorithm itself. The selection and ranking method consists of the following steps. First, we extract all the candidate monosemous relatives within 4 steps from a target polysemous word. Then we compile the synseth nest of the target sense. And then, for each candidate monosemous relative, we find 100 most similar words according to the word-to-vec model trained on the corresponding corpus. We then intersect these top 100 words with the words included in the synseth nest. The final weight of the synseth in the synseth nest is determined by the maximum weight among all the words that represent the synseth in the intersection. The total score of the monosemous candidate is the sum of the weights of all the synseth from the synseth nest. So the final weight of the candidate can be defined as follows, and the formula is given at the bottom of the slide. So our method implies that more scores are assigned to those candidates that resemble a greater number of synseths from the synseth nest. The following fragment of list of monosemous relatives with respective similarity scores that are given in brackets were obtained for the noun gvozdika in its 2 senses, carnation and club. We see that all monosemous relatives are sorted by the weight that they obtained. The higher rated monosemous relatives are supposed to be better candidates to represent the sense of the target word. So their contexts are best suited as training examples in the word sense disambiguation task. So once we have selected the monosemous candidates, we can extract from the corpus the context in which they occur. Then we substitute the monosemous relatives with the target ambiguous word in this text and add them to the training collection. We used 2 described corpora for compiling such collections, the use corpus and prosa.ru corpus. In our research, we implemented 2 ways of creating training collections. based on the monosimous relatives rating. We compiled the first collection only with the monosimous relatives from the top of the candidate rating. We wanted to obtain 1,000 examples for each of the target words. So for the simplicity, we will call this collection Corpus 1000 because we obtained exactly 1,000 examples for each sense. As for the second methods, the training examples for the target ambiguous words were collected with the help of all respective monosimous relatives with non-zero weight. The number of extracted contexts for a monosimous candidate is in direct proportion to its weight. And accordingly, we named this collection a balanced one because we used all the respective monosimous relatives. We conducted several experiments to determine whether our text collection can be used as a training data set for a word-sense disambiguation model. In our research, we used Kanier's neighbor classification algorithm based on contextualized word embeddings Elmo and Bird. In our experiments, we exploited two distinct Elmo models. The one trained by Deep Pavlov on Russian WMT news, and the other is Rus Vectoris lemmatized Elmo model trained on Taiga corpus. From the first model, we extracted a vector for a whole sentence with a target word. And for the second one, we extracted a single vector for a target ambiguous word. We also used two BERT models. The one is BERT multilingual by Google Research, and the other is RUBERT by Deep Pavlov. It was pre-trained especially for Russian language. To extract BERT contextualized representation, we concatenated the representations from the top four hidden layers. Next in these tables, we demonstrate the results obtained by different types of contextualized word embeddings, different training collections, and model parameters. We can see that all systems surpass the quality level of the baseline solution trained on the data set of the dictionary definitions and usage examples. The algorithm based on Elmo pre-trained embeddings by Rus Vectoris outperformed all other models, and the best result is 0.857 F1 square. The second model in all the collections is Rubert by Deep Pavlov, followed by Elmo model by Deep Pavlov, and the lowest F1 score belongs to multilingual Barrett. So as for the differences between the Corpus 1000 and the balanced collection, we can observe the minor performance drop for the Corpus 1000 for all the models except for the Rubert. We can see that Corpus 1000 doesn't include all the possible monosimous relatives, so it lacks contextual diversity. The balanced collection, on the contrary, is more representative with regard to the variety of the contexts. So now for our additional findings, we can see that Prosa.ru achieves better results and outperforms the news training collection. The model trained on the news collection achieved lower F1 score because of the lexical and structural differences between training and test sets. We know that the examples in the test set are taken from Russian National Corpus and Wikipedia, but training collection were composed of the news articles. On the contrary, Prosa.ru consists of various works of fiction. So the Prosa.ru training collection has more similar word representations to the test ones. And thus we conclude that similar genres of training and test collections give higher results in the word sense disambiguation task. So On the slide, we briefly overview the results that I have already demonstrated. And now to the conclusion. The issue that we addressed in this article is the lack of the sense-annotated data for the Russian language. In this report, we have described our algorithm of automatic collection and annotation of training data for the Russian language. The main contribution of our research is that we have considered in selection and ranking algorithms a wide range of monogamous relatives types. We also utilized the metric based on a Kazan similarity to determine the most appropriate monogamous relative to be added to the training collection. Also, in order to evaluate the training collections, we applied K-nearest neighbor classifier to the contextualized word embeddings and measured its performance on the Russia-RUNet test dataset. The best result was obtained with Rusvectora's ELMA model and Proza.ru training collection and amounted to 0.857 F1 score. And we have also found that the better performance of the word-sense disambiguation models is achieved when the genre of the training and test collections match. So that's all for now. Thank you for your attention, and we will be glad to answer your questions.
We have one question in the chat here from Petya Optimova. How much time did the best model take to train?
So it depends on the number of the training samples, and in our case, it took about 2 hours to extract all the vectors for the target words, and then the inference is quite fast. It takes around 10 minutes, I guess.
And Maria Gritz also wants.
Yes, thank you very much for your interesting research. My question is, do you consider using knowledge bases, for example, ontologies, in order to broaden the scope of monosemous relatives?
So for now, we use only Russian thesaurus, RUNet. I don't think that in any future research we will use any other resources, but maybe it would be a good addition to our method.
Thank you.
But for now, we're only working with the Russian thesaurus.
Thank you.
Another question from the YouTube channel. Retro thank you for the interesting talk. Do you distinguish harmony and polysemy?
Well, I can't hear you well. Once again, please.
The question is, do you distinguish homonymy and polysemy?
Well, in our research, we do not have any homonyms. We used only polysemous words. Well, I guess the one word can be a homonym. It's the word zamok in the mean castle and the lock. But all the other words are polysemous.